Good morning. Welcome to our science seminar for today. We're happy to have a joint science seminar between the School of Arts and Science and the School of Engineering and Engineering Technology today. And so to further catalyze that, I'd like to introduce our introducer. Our introducer today is Norman Reese, okay, from the School of Engineering and Engineering Technology. Let's give him a warm welcome.
You've heard it said that the most important things are caught and not taught. And when I was a student here at Laterno University, I got the opportunity to participate in a co-op program. So that means you actually get, every other semester I went and worked at NASA at Johnson Space Center. And if some of you can do that, I strongly encourage you to consider that or take a semester internship. I mean, this really changes how you do what you're learning here. But I got the chance to go down and co-op and worked at a couple different places there at Johnson Space Center. And some of the places I worked, I don't want to be like this manager, okay? I don't want to be like the people that work in this group. And so it gave me a chance to look around because I was looking for a mentor, right? I hope you found somebody maybe here at Laterno to like, I want to learn from this person, I want to be more like this person. But I got a chance to work in structural design and test. And my boss was a man named Kornel, Dr. Nagy, who now got to come and speak to you. But he was a guy that's like, man, I want to be like him. And the people that worked for him were leaders, they were enthusiastic, they were competent, they were respected. Like, I would like to work in his department. And God worked it out so that I could. And that was a couple decades ago. Dr. Nagy actually escaped communist Hungary, and in the 1950s, he was 17 years old, got across the border, got a visa to America, came here, learned English, eventually went to University of Houston while he worked. He studied at night, worked his way through a bachelor's degree and a master's degree, and then went on and got a PhD there at University of Houston, and got hired at NASA in 1968. He started at a contractor in 68, got hired at
74 with
74. NASA. And so he's been working in the aerospace industry for 51 years. He turns 80 this year and loves it. And that's in itself a testimony. Like some of us, like, I just want to stop working. I want to get rich and quit working. And he's got a different perspective on that. So let's welcome Dr. Kornel Nagy.
Let me adjust the screen to a lower setting here. Sorry, I'll move a little. Blank screen now.
Is it blank?
Yeah, that's the blank issue.
It's a funny thing.
Uh-oh, we got a wiring.
Yeah, it's got a wire trouble somewhere. Here, let's
Is it powered on again? No, sometimes it will. It's doing auto power on.
It's powered on, but it's white.
Yeah, it's.
And now I just repowered it.
It came. It's back.
Back.
It's good. I gotta pray.
Yeah. we didn't.
We prayed. We should have prayed.
Thank you very much for inviting me. And of course, what I have in my presentation is basically the next future challenge for our country and for humanity is deep space missions with crews. And what you have on the cover sheet is the current concept for the Gateway Space Station, which will be a lunar space station, you know, built by our country, and also other countries will participate. And this will be the waypoint to take and then do surface missions to the moon. And also this station will be the waypoint to do missions to Mars later. And let's see.
Working. Oh, yeah.
Am I pushing the right button?
Just to be turned on here. There you go.
Oh, thank you.
There we go.
And basically the focus is really to highlight to you the technical challenges that we'll be facing, you know, to take and then do the missions, you know, lunar orbit and in deep space. And the reason for my methodology of highlighting them is really to show you that they are not mysteries. They are basically challenges that we'll be able to overcome with a lot of hard work and a lot of design work, and then they are very doable. But I will point out some of the difficulties, that we'll be faced with. And to date, the only deep space mission we had is the Apollo missions. That's kind of the historical record. And then the current proposals are that we're going to have missions to the moon and missions to Mars. And in this year's federal budget, Congress and the President included funding for the Gateway. And then basically now NASA is authorized to start building the Gateway hardware and do all the work required, to make it a reality. And your scheduling of your degrees is perfectly timed for one of the greatest missions, engineering missions that's coming up, is the deep space missions, the moon and Mars. And then you're going to be getting in right on the ground floor, right at the start. So it is very exciting times, and then let me kind of proceed and then talk some of the details. The one point I make on the bottom of this chart, that all the low Earth orbit designs for spacecraft will have to be modified for the deep space environment. You just cannot do carbon copies. We're doing the same technology, similar technology, but it has to be certified for deep space, which is radiation environment, the thermal environment, and so forth is much more difficult. And I just included a chart to recite, the Apollo missions. Basically, we had 6 landings. Apollo 13 did not have a landing, because of the accident, the mishap that we had. And mishap is the politically correct, nice way to say an accident. But basically, we had a hardware failure, but the crew was able to survive using the resources for the lunar lander, the LEM module. And, there was a movie, Apollo 13 movie, documents it. Last summer, my kids got me the gift of viewing the Apollo 13 movie at Jones Hall in Houston, because the music score was played by the symphony. And so to me, that is an absolutely emotional movie, points out the strong need for us to do our design work and development work without failures. First landing was Apollo 11. The last landing was Apollo 17. And basically, we got some samples, and I have the kind of trajectory images on the chart, and the command module images, and the lander images. And I also included the landing sites, where we landed on the moon, that were chosen, for various scientific objectives. On the current proposals to go to the moon and Mars, there's a phased implementation that's being proposed, and then the space launch system and commercial launch vehicles will be used, to launch all the elements. And then the Orion's crewed spacecraft with command module and service module, which is similar in design, updated, of course, to the current requirements to the Apollo spacecraft. And the Deep Space Gateway in cislunar orbit is the illustration that I have. Is, let's see, let me kind of describe the, in the corner of this one. So this one is the Orion spacecraft that will bring the crew, with the SLS rocket to the Gateway station when the crew is coming. And this is an airlock where they will be able to do EVAs from the airlock. And this is an inflatable module, pressurized module, habitation module. And this is a normal traditional habitation module with aluminum pressure shell. And this one is a utility module, basically, you know, for enables the docking of the logistics vehicle for refueling the propulsion system. And this is called an Esprit, and that's basically a science airlock, you know, for science experiments, and also basically the storage of propellants. And this is the power and propulsion module, which, by the way, uses Hall effect thrusters. So that's, you know, that Hall effect thrusters have been used in some of the spacecrafts, you know, by different companies in different nations. But for us, for NASA, it will be the first use of Hall effect thrusters. And again, that's again a key advancement, you know, for the new space station. The powers are solar arrays, you know, where we obtain the power. And the logistics module docks to the side and brings the supplies to Gateway. One of the challenges will be with the logistics is that, you know, on low Earth orbit for ISS, the logistics module is offloaded by the crew, and all the element, you know, all the hardware that's brought up is transferred by the crew inside ISS. On Gateway, the crew will be only there for 1 month out of a year, and so one of the strong needs will be is the invention of a methodology to take and then transfer the contents of the logistics module and stow it inside the Gateway. And that's, again, ready for invention. You know, when I saw the demonstration yesterday of the device to chase the ducks off the golf course, you know, that the folks demonstrated to me, I thought about it. I said, wait a minute. What if a device like that was invented to be able to pick up the storage bags, you know, inside the logistics module, transfer them into the Gateway, and stow them in the proper location? And of course, that's TBD invention. Right now, just an idea in my head, but I don't have an implementation idea. But to me, that's a challenge, because the crew won't be there to do that. And, you know, NASA developed Robonaut, you know, which is a robotic application. But to me, I'm wondering if, you know, one robot could do all the different tasks, you know, that are required. And maybe it would be an advantage for some of the tasks to develop a dedicated robotic device, you know, to do transferring of the logistics. Also on the Gateway, we have the Canadian arm. The Canadians will be developing a version. Basically, we had the shuttle manipulator arm, and I was the subsystem manager for the shuttle arm for structures. And then on the ISS, we have the Canadian arm, you know, for doing all of the manipulation and movement of the items. And then the updated version, you know, will be for Gateway, and they'll be providing that. Some of the international partners will be providing some of the elements, pressurized elements and so forth, and so it's going to be an international project. Now let me go back to my chart. Now, when the lunar missions are going to start, initially I think that there are some plans and discussions to have uncrewed lunar landers, you know, to the surface, do exploration. One of the strong scientific interests is that there were observations from lunar orbit of seeing some evidence of water down in some of the craters. And one of the big objectives will be for Gateway to take and explore the lunar surface for water, you know, in situ resources. And later on, projects would be, of course, can you have really making propellants on the surface, in situ propellant manufacturing. You know, there's been studies and papers published on that, but so far, no missions have been done to do that. And the other items I've seen for surface development, when we'll have habitats on the surface, one of the best methods of radiation protection is to take and cover the habitat with like a layer of lunar soil, about a foot thick, 2 foot thick. But in order to do that, it will not be crew members in spacesuits with shovels. It'll have to be some equipment. And I've seen some papers, some concepts of how to take and then collect the lunar surface material, how to place it, like for radiation shielding and so forth. So to me, for mechanical engineering and for engineering in general, the future is absolutely bright because the need is so strong. It has to be invented. It reminds me of the time when Edison invented the light bulb. He's famous for the light bulb. Nobody ever says a word about that Edison and his team invented the way how to generate power, how to distribute power, light switches and so forth. Edison has like 1,000 patents on all the details, and nobody ever talks about anything else but the light bulb. And so we are in a very similar situation. All of this equipment has to be designed, developed, certified, and flown. And that's so exciting for engineering. I mean, it is like, when Spindletop started the old production, exploration. And think of all the engineering since then. Think of all the engineering that has happened in space drilling. One of my son-in-laws is a designer working for a company that designed the big offshore platforms. And the